This brings us to traditional digital forensics relies on a single, tangible premise, securing a physical crime scene. Investigators isolate hardware, copy static data from dead drives, and analyze the resulting evidence in a lab. Cloud computing removes that physical anchor. The infrastructure is invisible, geographically dispersed across multiple data centers, and dynamically allocates resources. In these environments, system states change in milliseconds. Data exists ephemerally before being overwritten or deleted, making the process of pulling a forensically sound image of a physical drive impossible. This brings us to Topic 1, Introduction to Cloud Forensics and Crimes. The mandate for investigators has pivoted. We are no longer extracting localized binary files from a specific desk in an office. We have to parse live, distributed API execution streams traversing global networks. You aren't looking for a physical weapon left at the scene. You are tracing invisible network commands that dictate how virtual machines and storage buckets behave. Investigating the cloud means capturing volatile memory states and server logs in real time before the target infrastructure executes its instruction to systematically delete itself. The massive scalability and built-in anonymity of cloud architecture create ideal vectors for cyber attacks. Take mass data exfiltration. Attackers scan for misconfigured storage buckets and automate the theft of millions of customer records instantly, bypassing traditional perimeter defenses entirely. Then there is the threat of cryptojacking. Instead of stealing data, an attacker hijacks an organization's elastic compute resources to mine cryptocurrency. Because the cloud autoscales to meet demand, the victim's infrastructure expands automatically, draining vast amounts of money and usage fees before the breach is detected. Threat actors also weaponize stolen identity credentials to deploy ransomware. They can bypass endpoints completely and drop encryption payloads directly onto cloud-hosted infrastructure backups. And compromised cloud instances can be chained together into botnets, launching distributed denial-of-service attacks that exceed terabits per second. The cloud's primary feature, its massive automated scalability, is exactly what makes it the perfect environment for frictionless, devastating crime. We will now cover Topic 2, Cloud Forensic Challenges. Cloud architectures inherently block traditional collection methodologies. Investigators must navigate 4 specific structural barriers to extract actionable evidence. The first barrier is data jurisdiction. A single database might be fragmented across international data centers, each governed by conflicting privacy and localization laws. Second is multi-tenancy. A physical server is sliced into virtual layers. You cannot image the entire server without capturing uninvolved tenants. You must extract only the target layer. Third is resource volatility. Attackers spin up short-lived container nodes, launch attacks, and terminate them minutes later. Once that instance is terminated, the local disk data is instantly overwritten and permanently destroyed by the provider. Additionally, auto-scaling events during a major attack often mix log files across the shared infrastructure, leading to cross-tenant contamination of the evidence. The fourth barrier is encryption. Providers typically encrypt data at rest, adding a cryptographic wall to any raw storage volumes you manage to retrieve. Compounding all of this is the sheer volume of data generated across distributed nodes, making manual evidence identification computationally impossible. Because the physical hardware acts as an evidentiary black hole, investigators must bypass the physical layer entirely and target the cloud's control plane. This leads us to Topic 3, Reviewing CloudTrail Logs. In Amazon Web Services, CloudTrail acts as the definitive, chronological record of every API call made within an environment. These JSON API logs are the only reliable source of truth for tracking unauthorized activity. First, we isolate the user identity field to identify the role executing the command. Next, cross-referencing that identity with the source IP address maps the remote command back to a specific geographic endpoint. Sophisticated attackers know this. Their immediate next step upon gaining access will be attempting to alter or delete these logs to cover their tracks. To prevent this, security teams must automatically export their logs to isolated, immutable storage buckets in a separate, highly restricted account. This is known as write-once, read-many storage. It mathematically prevents any retroactive modification or deletion by an attacker, even if they have compromised the primary environment. Establishing a pristine chain of custody is a legal requirement. It ensures the collected logs meet the strict evidentiary standards necessary for admissibility in court. Cloud environments are built to be volatile and impermanent, but correctly configured API logs serve as the unalterable digital DNA of any crime committed. Our final topic shifts the focus to software as a service platforms. Topic 4. Investigating Dropbox and Google Drive. Obtaining server-side logs directly from a SaaS provider requires navigating lengthy legal procedures and international warrants, a process that inevitably alerts the provider and potentially the suspect to the investigation. There is a faster, covert alternative, bypassing the cloud provider entirely and targeting the suspect's local endpoint hardware. Sync applications for services like Dropbox and Google Drive are built on a specific operational principle. To function smoothly across fluctuating network conditions, they must cache vast amounts of data locally on the Windows operating system. The cloud's reliance on local client hardware creates a massive, silent vulnerability for criminals who mistakenly believe their remote cloud activity is untouchable. Even if a user uninstalls the Google Drive application and deletes all their synced files from the remote server, aggressive data remnants remain hidden deep within the local file system. Investigators navigate to the Windows App Data Directory structure to locate hidden SQLite databases left behind by the sync clients. This visualization shows the carving process. You isolate specific target database files, focusing explicitly on sync_config.db. Inside, you find critical metadata tying the hardware to the crime, account IDs, emails, and device names. Next, you extract the snapshot caching databases. These carve out a historical timeline of file uploads, modifications, and downloads. Parsing these tables reveals time-stamped flags indicating files the suspect actively attempted to delete from the cloud. The ultimate forensic benefit here is operational secrecy. This carving technique reconstructs a perfect timeline of cloud activity locally, without ever requiring investigators to issue a warrant or log in to the remote cloud interface. True cloud forensics is a dual-vector discipline. You must secure volatile infrastructure via centralized API logs, while simultaneously carving the persistent truth hidden on the local endpoint.